Hi everybody, welcome to Office Hours. I'm Nathan Rao, and I'm here to help out with your question on length extension attacks. And before we get into that, let me explain a little bit about some principles behind this attack, something that it's trying to attack, what's trying to defend against it, and what's built around it to give you some more information on how this is working and build some connections for this project that will help in your understanding. So first, we're really early into the unit, right? We're talking about cryptography, and there are three main principles we're talking about. We got confidentiality, sender authentication, and message integrity. And with message integrity, that is the one that we are going to be focusing on here, because essentially, let's say we have a sender Alice and a receiver Bob, and if Alice is trying to send a message to Bob, Bob would know if the message has been modified. It's this idea that whatever message we are sending to another person, that person can verify if it's been modified. Basically, your messages cannot be modified without you knowing. So that's what message integrity is trying to protect, is that your messages can't be modified. And what we talked about in lecture was pseudo-random functions, right? Or these cryptographic hash functions. Those are the idea, essentially, that with this random set of functions, we have a key that chooses one of those functions, and with that, we have an input. This is our message. This is what we're trying to send. We put that into the function. We get an output. This is a hash, and that other person on the receiving end will have this hash, the message, and the key, and they'll make sure that that message gives out a hash that is equal to the hash that was sent. That is essentially how this is going to work out, right? And one really important thing to remember about hash functions is that they're one way. You cannot go backwards. Essentially, if I put an input and I get an output, you cannot know what input it came out to. Basically, they're one way. You cannot trace them back. There's no map between them, okay? This is different than encryption. Just keep that in mind. Encryption and decryption, the process between that is that you can go back. That's the point of it, is that you have an input, you encrypt it, and then if you use the decryption function on that, you'll get back to the same input. That is the point between that. Very different from SHA, and they protect different things. But for the purposes of right now, we're talking about SHA. This is the hash functions. These are protecting against message integrity. And I kind of spoiled it. We're talking about SHA specifically for this, specifically SHA-256, because SHA-1 and MD5, these are broken hash functions. And I'll explain later what that means. But talking about SHA-256, and let me draw out a little bit of a diagram to explain how this is working. So these are compression functions, SHA-256, and essentially you have this already known original input, original, like, I guess, kind of like, it's kind of like an input. It's the why not. It's essentially the constant that's always going to start off with the first base that's being compressed, and then you keep adding more bases with whatever that output is. And this will make sense after I draw it to you, if you didn't understand already. But essentially, your message can be as large as it needs to be. It is split into 512 chunks, though, 512-bit chunks. And you keep splitting them up, and then if you have less or extra, or not even extra, there will always be padding added to the end of that to indicate where the message ended for one. Also help out with the identity that you cannot have equal break down hash collisions. We'll talk about that in a very quick sec later. But this is what it's building upon. You keep adding the bases, you break them into 512-bit additions, and you keep hashing it with whatever was the output from the previous one. So drawing this out, it will look a little blurry, and it might look backwards because of cameras, but on that note, I'll point out to it. So we have a base right here. This is the first part of the message getting put into the compression function H with this original constant y naught. This gets hashed, then we get this y1. This is the original compression first, and then we put any extra messages, compress that, and we keep going. So that's how this function works. You're going to just keep breaking the message down and keep adding parts of it into the compression function until the end. This is the Merkle-Damgard construction model, and this is how SHA is working in this instance. And you might have already kind of clocked what's going on here, but you might be seeing, oh, is there a possible vulnerability with here? And that's kind of what length extension attack is going for right here. And you can see we can keep adding messages, new parts of messages, as long as we have the original hash output from the past stuff. And that's kind of what this is going for. I mean, this is what it's going for. So in the context of a basic length extension attack, if because you're trying to send the message and the verifier, right, to the reader, and this attacker in the middle, which we're going to call Mallory, Mallory is going to get this token, which is the hash, and then also the message. And because Mallory has access to that, and let's say Mallory also has access to a key, or not the value of the key. You do not need the value of the key. You just need the length of it. But if Mallory knows the length of everything, Mallory can deduce what this hash output is going to be, right? So we already have the original hash, and we know the size of a potential key, the size of the message, and based on that, you can calculate how much padding there is going to be for the whole hash. So you have all of that. You have the original hash, and then according to the Merkle-Damgard constructor, why not I just add a new base? And that's exactly what this attack is doing. So let me write this out for you. So let's say the original V is equal to the hash of a key and a message. So that's the original one right there, right? And so in the attack version that we're trying to add, we want to add a suffix. We're going to call this suffix S, and this is going to be our attack. And essentially, because we need to add a new base, we need to hash the key, the message, and that suffix. And that is essentially what we're going to be hashing. But I made a little bit of a mistake here, right? Because you'll be thinking, okay, was that everything that was added to the hash? And that's not true. Remember, every message, if it's every message regardless is going to have padding, and you have to make sure to add that padding to this hash. Otherwise, you're not going to have the correct hash message at the end of it, and the verifier is going to catch that on Bob's end. So make sure that when you're doing this verification for V prime, it's going to be the hash of your key, your message, the original padding, and then that suffix that you want to add. So just to clarify right here, at the very bottom, you got to add the hash of the key, the message, the padding, and the original suffix. This will be sent to Bob, and Bob will not be able to know that this was a different sender. Bob's just going to think it was Alice that sent this, because the verifier is going to succeed because of the Merkle-Damgard construction. There's no changes that happen to it that Bob can't recognize. So that is essentially how this attack is working. And you might be wondering, that seems very powerful. How am I supposed to overcome this? And the method that we've been using in the industry is HMAC SHA-256. HMAC SHA-256, message authentication code. That's what the MAC stands for. Essentially, there's a lot of XORs and extra hashing that goes in with the message, and this makes it hard to append a new message onto it. So for that reason, we use that, and that combats this problem. You can no longer append messages because of the different structure that goes within. I saw you guys had another question. Oh, that's a great question. And the question was essentially that SHA-256, this is such a big vulnerability. Why is this still useful, and why is it not bad like SHA-1 or MD5? And that's a great question. And this goes back to the other principle, which I was talking about one way, right? This function can only go one way. And SHA-1 and MD5 are broken for this reason, because they violate the three principles of cryptographic hash functions: pre-image resistance, collision resistance, and second pre-image resistance. And let me just clarify those for you pretty quickly. So we got pre-image, and it's the idea that if I'm given an output H hash, I cannot find a message for this hash that is that has that hash. So if I have an output, I cannot find a message for this output. So that's what pre-image is. Collision, it's essentially the idea that I cannot find two messages that have the same hash. That's what collision is. Basically, it's a collision, right? There are two messages with the same hash, and that's a problem. We can cause some mistakes with that. And then the last one is second pre-image. It's the idea that if I have a message, I cannot find a hash that has that same message. It's very similar to collision, but I'm given more things, right? So I cannot find that. So yeah. So again, to recap, I cannot find a hash that is equal to a different message's hash. I cannot find two messages with the same hash, and given a message, I cannot find another message with that hash. So in the identity of SHA-256, it has not broken these as far as we know. There is no way to solve it in that way, but for MD5 and SHA-1, it has been broken. People have been able to find messages with similar hashes and violate the principles, which makes them not one way anymore because we can go back the other way. So I hope that answers your questions. I hope you got some insight on how linked extension attacks work. And if you do not have any other info, I wish you the best. But if you have extra questions, please come back to another session or sign up in the queue again right now today. I have some time. Also, can reach out to me on Piazza. We love to respond to you guys on Piazza. So please reach out then. But thank you guys, and I'll see you later.